The ideal gas law. Well, in order to talk about the ideal gas law, we first need to know what makes a gas ideal. Okay? Well, there are two things. Okay? Gases are considered to be ideal if they are at high temperatures. Okay? Now, we consider room temperature to be a high enough temperature. Okay? So room temperature higher, that's considered high temperature. Okay? It's also considered an ideal gas if it's at a low pressure, okay? And we consider atmospheric pressure to be a low pressure. So right now, if you're sitting in a classroom, got air, okay, that air is an ideal gas. It's at room temperature, which is high enough, and it's at atmospheric pressure, which is low enough, okay? Now, once you have an ideal gas, these ideal gases can be completely described by three things. Okay? Their pressure, their volume, and their temperature. Okay? The macroscopic state of them can be completely described by those three things. And the ideal gas law is used to relate them. And the ideal gas law is the equation that says the pressure times the volume is equal to the number of molecules multiplied by Boltzmann's constant multiplied by the temperature. Okay? And this temperature needs to be in Kelvin. So how do you get your temperature to be in Kelvin? Well, you might have to convert it. So if you need to convert your temperature to Kelvin and it's in Celsius, you simply take that number and add 273, and typically we add 273 and 1500ths, okay? But if you just add 273 for this class, that'll be okay. All right, so we've got this equation. Now, typically, we don't actually use this equation. What we do is we take this equation and we make it a little more beneficial for the problems that we are going to see. Okay, so we're going to take this equation on the next page and make it a little more beneficial. Okay, so our equation says this. Pressure times volume is equal to the number of molecules times Boltzmann's constant times the temperature. Okay. What we're going to do this equation is we're going to rearrange it. We're going to solve it. Okay? We're going to solve for Boltzmann's constant, which means I need to divide both sides by the number of molecules and the temperature. On this side, it cancels, and I am left with pressure times volume is equal to the number of molecules times the temperature, and that equals Boltzmann's constant. The reason we're doing this is because this is Boltzmann's constant. It's a constant, it does not change. So I can do this for a situation. So let's say I have a piston, okay? A piston is like a nice cylinder, okay, with a plunger. Okay, so for situation number one, you've got a gas inside this piston. Okay, that gas has a certain pressure, a certain volume, there's a certain number of molecules in there, and it's at a certain temperature. Okay, now I'm going to take this plunger, and I am going to push it down so that the volume is no longer as big. Okay, and this will be situation number two. Now in situation number two, we can go ahead and solve this equation again for Boltzmann's constant, and we'll end up with pressure 2, volume 2, divided by the number of molecules in situation 2, times temperature 2 is equal to Boltzmann's constant. Now if we look at these, they're both equal to Boltzmann's constant. Okay, if you remember the transitive property, talks about it a little bit in algebra, talks about it a bunch in geometry. Okay, if A equals B and B equals C, then A equals C. So we're going to use the transitive property of equality here to set these two equal to each other. I have pressure 1, volume 1 over the number of molecules in situation 1 times temperature 1 is equal to pressure 2, volume 2 times the number of molecules in situation 2 times temperature 2. And this is a much more useful equation for us. Now, in reality, what's going to happen is a lot of times the number of molecules is going to stay the same from the beginning to the end in both situations. And when that happens, if N1 equals N2, okay, if that doesn't change, then I can substitute N2 in over here, multiply both sides by N2, okay, and we're going to end up using this equation. Pressure 1, volume 1 over temperature 1 equals pressure 2, volume 2 over temperature 2. And you've probably seen this equation in your chemistry class. Now, if the number of molecules does happen to change, we need to put it back in there. If these two are not the same, we can't solve it and get our second equation.